exercise, which is exercise number 42. And the exercise asks, what kind of coding tree is built by the Huffman algorithm if the alphabet consists of n characters having the frequencies of the first n Fibonacci numbers? All right, so before doing it, let's think about it, how it can look like. So without really doing it, we could think about it, how it could look like, or what it looks like. I'm going to stop sharing and opening a whiteboard here where we can write and draw and so on. And remember that the Fibonacci numbers are 1, 1, 2, 3, 5, 8, 13, 21, and so on. Each Fibonacci number is the sum of the two previous Fibonacci numbers. Now there are many identities, many equalities on these on this series or on this sequence of numbers, and one of them is the following. It says that the sum of all Fibonacci numbers from the first to the nth is equal to the n plus second Fibonacci number minus 1. How can we prove it? We can prove it, for example, using mathematical induction. Do you know what mathematical induction is? Well, not all of you. But never mind, it's very easy. To do a mathematical induction here, we simply prove it for n equals 1. If n equals 1, then this equality here, this one, this is what we want to prove, then this will change to the form 1 equals, and f here, fn plus 2 is f1 plus 2, that's f3, and f3 is here. f3 equals 2, so this is 2 minus 1. Well, I think that everyone have to admit that this equality holds. 1 equals 2 minus 1. And now, simply using the original equality, we are going to prove that if that holds, then it will hold also for 1 n more. That means that then the identity, the sum of the first n plus 1 Fibonacci numbers equals fn plus 3 minus 1. Is this true or not? Yes, because if we assume that this equality is true, then that means that this sum, this sum can be broken up into two parts. The sum which goes only to the nth Fibonacci number, and we separately write fn plus 1. But we know by this original equality, which we assume now to be true, that this sum equals fn plus 2 minus 1. It's okay, but together fn plus 2 and fn plus 1 together will, if we add them, this will be equal to fn plus 3. And here we have n plus 3, here we have minus 1. So that means that fn plus 3 minus 1 is really equal to that sum. So, all right, that's all. That's a short mathematical proof, but the main thing is that what we have proved now is that this equality holds. Why is it important for us? All right, I'm trying to erase the rest here now. Okay, so this is true. Why is it important? Because if we are trying to draw the binary tree of coding for the Huffman codes over a file where the frequencies of occurrence for the particular characters form the Fibonacci series, then in the because of the way how the Huffman coding algorithm works, at each stage we have the sum of some Fibonacci numbers. And certainly if we, okay, that's okay. And certainly if we have a certain part of the Fibonacci numbers here, then this is the sum of some Fibonacci numbers. For example, this is now the sum of the first 5 Fibonacci numbers. And we know by this identity here, this equality here, that this is then equal to 13 minus 1. That's 12. This is 13, and this will be 1 less than 13. Why is it important? Because if at a stage the first few or first some Fibonacci numbers are in a subtree of this tree of coding, then the merged element which will substitute these elements in the tree has a label 12, a label of 12. But that means that the two rarest elements or characters in this virtual file are 12 and 8. 8 is certainly because it is less than 13, because it is the left neighbor of 13 in this series, and 12 because it is less by 1 than 13 due to this identity. So that means that the Huffman coding's tree will look like something like this. And so on and so on. So it will be very long, like this. That's because of this. So if at any stage you have, here you have the sum of some Fibonacci numbers. Sorry, I have forgotten here. Here I have one more. Yes, these are the ones, and that's then 2, and this is 2, and this is 4, and so on. 1, 1, 2, 3, and this is 7. That's what's this? That's 5. Here are the Fibonacci numbers. So these are the Fibonacci numbers. These. This is 8. This is 13. And here we have the merged ones. 5 plus 7 plus 5 makes 12. That's 12. That's 20, and so on. But if you do not believe me, then we can change to our software here, and we can change the text. And we say that the first Fibonacci number is 1, the second is 1, the third is 2, then comes 3, then 1, 2, 3, 4, 5, then 8, 1, 2, 3, 4, 5, 6, 7, 8, then 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, and so on. If we build this tree, then you will see that that's what exactly is happening, what we have predicted by that formula on